Hello. So right now for this video, I'm going to try to show that much of math is really just different ways to add things together, from just addition to more complex forms such as integration, derivation, and even more. So starting off with addition, 6 plus 6 equals 12. What does this mean? Well, 6 and 6 are two different groups, and we combine them to get a combined value of 12, or there's 6 units of something, and it makes 12 units. What about for subtraction, though? Well, for subtraction, we can see that like 6 minus 2 is equal to 4. We can see that this is really just 6 plus negative 2 is equal to 4. So you're really just adding negative numbers. And to put this into perspective, to just give a visualization, let's just say 0 to 6 plus, 0 to 6 right here. So this is like, for example, right here, 6 plus 6 equals 12, gives a combined value of 6, 0 to 12. This is not drawn to scale, but this would be double the length of the other two. But for subtraction, we would have something like 0 to 6 plus our 2 value, but it's going in the opposite direction, 2, and that gives a net total of 4, or 6 plus negative 2 is equal to 4. Moving on to another unit, let's go to multiplication. So we know that 2 times 6 is equal to 12, and of course multiplication is commutative, so it doesn't matter whether it is 6 times 2 or 2 times 6. So 6 times 2 here. But what does that mean in terms of addition, though? That's what I'm trying to show. Well, we know that 2 times 6, is really just 2 plus 2 plus 2 plus 2 plus 2 equal to 12, and then this is done 6 times. This could also be viewed physically or geometrically by like units of 2 times units of 6, and that gives an area of 12 as another way to visualize this. But this is really just adding a number. Multiplication is really just repeated addition. And of course we can also do this, since it's commutative. 6 plus 6 is also equal to 12, and this is done 2 times. Moving on to division, something that is not commutative, aka it matters where it is done from. So for example, 10 divided by 2 is equal to 10 over 2, which is equal to 5. But what does this mean? Well, it's really subtracting 10 by 2 5 times. This is done 5 times. And we can see that there is no remainder for this. But we could have a remainder, for example. Let's say 10 divided by 3. This is 10 over 3. This would be 10 minus 3 minus 3 minus 3, and this is equal to 1. We have a remainder of 1. This is done 3 times. So we know that 10 divided by 3 is about 3 point something. Well, we have a remainder of 1, with this is being divided by 3. So we know that this is really 3 and 1/3. This could be a mixed number, but since 3 times 3, a mixed number does kind of look like 3 times 1/3, which is, I don't want to get confused by that or anyone else, so leaving by 3 and 1/3. But of course, 1/3 is a decimal, which is 0.33 repeating. So the answer would be 3.33 repeating. We can then show this again, 10 divided by 4. This is 10 over 4. We can see this by saying 10 minus 4 minus 4. This is equal to 2. This is done 2 times. So we know that 10 over 4 is about 2 point something. We'll say 2 point something. And we can see that this is a remainder of 2. It's being divided by 4. So it's really about 2 and 1/2. 1/2 is equal to 2.5, which we can show by 4 goes into 10. How many times? 2 times, of course. This is 8. We have a remainder of 2. Bring down 0. 4 goes into 20 5 times. So we see it is 2.5. Moving on, we can see, now to put this into a physics perspective, I guess, we can say that mass equals rho times volume, or the density is equal to mass per some unit volume. Well, we can see that this is a multiplication problem. We just did multiplication before, so we already know this. This mass is really equal to volume 1 plus volume 2 plus something, and this is done rho times. Just looking at the physical units, this. Like down below, and it's commutative, so it can also be like rho 1 plus some rho 2 plus repeating. This is done volume times. But what happens if this unit right here isn't constant? What happens if instead of 2 plus 2 plus 2 plus something, it's like 1 plus 2 plus 3 plus something, like 5 plus 10 plus something, something, something. The point is, what happens if the addition is changing at each individual element or unit? Well, that is when we can go into calculus, if you will, and we see something called the volume integrated over this entire volume, dv, where v is not constant. But, of course, if v was constant, then we'd see it's rho times v, where v is equal constant. So integration is really just multiplication, but a variable is changing. And we can see this a little bit more clearly too, because like, for example, if we were to have calculus, 2 times 6, so equals 12. That thing that we were talking before. Well, let's say that change 2 into y, for example. If we were to put this onto a graph, we have x by y. That y is going to be looking like this, y equals 2. It's constant. But we know that that's not always the case, right? You could have an exponential. You could have a linear graph like this. You could have so many more. The point is that there's a lot of times in nature or in math where things are changing. So let's go back to that integral notation that we were talking about. What is this supposed to mean? Why did people make this? Well, this was made because, well, let's look at the word sum. And then essentially this person looked at this. I remember learning about this in my calculus textbook. They looked at sum and they were like, oh, let's just elongate this. And then we got the integral sign, or sum. So let's talk more about how this is really just addition in a way. Here is the normal integral by dx. And this is equal to the limit as n approaches infinity of some notation. This is just saying this sum is just saying sum everything from 1 to n, some value n of xi times delta x. Delta x is the width. This right here is the height. The width and the height of what, though? Well, going back to those graphs, if we had some random unit right here, let's say, and we were to have boxes, just rectangles, I mean, right here, like this. This right here is delta x, just the width of whatever these rectangles that we're looking at. And the height is just taken at some point, and this would be f of xi, which is whatever point that is. Now we know for multiplication, as we had talked about previously, right here, where this can be visualized as a rectangle in a way, we're doing the exact same thing here. We don't know how to find the area under this curve, but we can't find the area of a rectangle, so we do that. But we can look at this right here. What happens if these n amount of rectangles get smaller and smaller and smaller, where we had this again, but these rectangles just kept getting smaller and smaller and smaller and smaller and smaller? Well, it approximates the curve better and better and better. And so you just keep adding up all of these rectangles, and inevitably you get the sum underneath it, aka sum being the key word here. Here, let's give an example here. Let's say f of xi is equal to f of x. This is going to be equal to x plus 1. That graph is going to look something like it's a linear graph. So we're taking and we'll take it from 0 to 5, 1, 2, 3, 4, 5. We're getting 5. So n is equal to 5 rectangles. Well, what does this look like? Well, we know I is equal to 1, n equals 5, because that's how many rectangles we were adding together. This right here is the function we're looking at, x plus 1. It's that graph under right there. What is the width? 1. Well, now we have these, so let's add them together. This is going to be equal to delta x times f of 0 plus f of 1 plus f of 2 plus f of 3 plus f of 4 right here. And excuse me, I have to get this delta x. It's from b a over n. This is going to be equal to 5 minus 0 over 5, and this equals to 1. Why? Because it's taking from this endpoint to the first point divided by n. It basically gives us the width right here of each of these. Right under here, as can be seen, delta x, the width. So we know this is equal to 1. This is equal to 1. What is f of 0? We plug 0 into x. That's 1 plus f of 1, plug there. 2 plus 3 plus 4 plus 5. And now, just like the other we're talking about right here, what if we had something like this? Well, if we add these together, multiply it by 1, that's going to be equal to 15 here. So we sum this area underneath this curve. And of course, we have a little extra right here, as you can see right here. So if we were to take the integral of this, x plus 1 dx, I'm just going to do this quickly. We get 1/2 x squared plus x from 0 to 5. This is going to be about equal to 12.5. So as you can see, this is a bit smaller than this, but they're pretty close overall. It was a good approximation. And this then concludes this, I'm trying to say, but overall, the integral is really just summing a bunch of units. So it is a different way to add things together. And this can even be seen with the derivative of dx dy, is really just change the division of something that is changing. Anyhow, and of course, changing division is really just repeated subtraction, and subtraction is really just adding negative numbers. So anyhow, thank you for listening. I hope you learned something. If I got a mistake, please let me know in the comments below. Thank you so much.